In this video, we're going to go through the answer keys for the first chapter 12 in-class exercise. And here's question 1, where we're going to just look at a series of reactions and where we're taking the standard electrophilic aromatic substitution reagents and reacting them with very symmetrical benzene rings. The idea, or the objective in this exercise, is just to be able to draw the products. All these benzene rings here are symmetrical. We're going to take up in the next exercise the orientation when we have substituted benzene rings. So let's just look at this one first. Okay, so let's take care of the simple, just completing the reactions. Let's look at reaction 1 here. If you look at this reaction, okay, you can see that it's obviously, I haven't put the pin up. There it is. Okay. It's the Friedel-Crafts Isolation is the name of this reaction. Okay. And in the Friedel-Crafts Isolation, all that happens is we take a hydrogen of the benzene ring. All the hydrogens that are on the benzene ring, remember here, are equal. There's one up here also that's exactly like it. And we're going to replace it with the R group of the acid chloride. Okay, so hydrogen's going to go away, and all of this stuff over here is going to become part of our molecule. All right, let's look at that. So here is what we predict as our product. Okay, the compound that you see there. If we had to look at the mechanism for this, all right, we would just make the acylium cation by taking a lone pair of chlorine. The aluminum chlorine bond is very strong, so this reaction proceeds fairly readily. Okay, so negative charge at aluminum, positive charge at chlorine. Now one of the oxygen lone pairs comes in, kicks that out. This makes the acylium carbocation, which is resonance stabilized, and then our benzene ring does a nucleophilic attack on this carbocation. Let's remember to just draw the hydrogen there, like so. Okay, this is I'm going to draw the product upside down relative to how it is there. Okay, that gives us that. Carbocation is there. And we'll just have a chloride ion come along and make some HCl. And that gives us our product. Okay, in this one, what we do is we take a hydrogen, and this reaction is nitration. And the net result here is that we replace hydrogen with NO2. Okay? All right, so all the hydrogens here are equal. And what we're going to do is we're going to just take one of those hydrogens, and it's going to be replaced with an NO2 group. Oops, yeah, right. And that should be the product. We could have replaced the other hydrogen too, but they're equal by symmetry, so it doesn't really matter which one we replace. And this goes through a very similar mechanism like the one before it. Just what happens here is that this combination of reagents, that's really a linear molecule, makes the nitronium cation. Okay, right there. Okay, the nitronium cation is made. It's going to now attack the benzene ring. Or the benzene ring is going to attack it, rather, since the benzene ring is the nucleophile. All right, sorry, I'm running out of room to write here. Okay, so this is going to give us H, N, okay, we'll get a carbocation here. Sorry, yeah, I'm going to have to erase that. Okay, so that gives us a carbocation there. And we'll just have some a nucleophile in the system. We'll say NO3 minus, maybe something like that. It's going to be the oxygen's the nucleophile, and that's going to attack and give us that. All right. Okay, so that gives us the final product right here. All right, the last one here is an example of the Friedel-Crafts Alkylation. And remember that in the Friedel-Crafts Alkylation, what happens here is we take a hydrogen and we're going to replace it with the whole R group attached to the chlorine. Okay, all right, so here's the product here. Okay, it's a symmetrical molecule, so we should see the cyclohexane ring attached to the benzene ring. Okay, I won't go through the early steps of this mechanism because it's the same as the Friedel-Crafts Isolation, kind of. Okay, we're going to make a carbocation. Okay, so we'll have the cyclohexylcation, and the new benzene ring is going to be a nucleophile. All right, this is going to attack here. All right, positive charge there. And in the last step, we'll just have chloride ion remove that proton. Sorry about that extra line there. I'm not sure what sort of computer glitch causes that. Maybe me moving the pen too fast or something. But once that hydrogen is removed, you can see how we're going to have the same final product that we have there. Okay, all right. So those are three of the key reactions: Friedel-Crafts Isolation, Friedel-Crafts Alkylation, and Nitration. Let's look at some others. This reaction here is sulphonation. And in sulphonation, what we do is we take the H and we're going to replace it by SO3H. Okay, so both of the hydrogens here are equal, and the product that we should see is the sulfonic acid you see here. If we want to really draw this group out, it's technically like this. Okay, if we look at the mechanism, what we do is we make that strong sulfuric acid is going to just protonate the system. This is going to now give us this intermediate right here. And this is going to lose the extra proton. Okay, sorry, I've got to figure out what does that. And that is going to give us the product up there. Okay, all right. So this next one looks like a two-step, and we're going to have to consider both steps. Number one is just another example of the Friedel-Crafts Alkylation. Which, remember, takes a hydrogen here and replaces it completely with the R group. Probably you should have the bromine, this should probably be aluminum bromide. You usually have the halogens match in this reaction. So the first reaction is going to afford this compound with a T-butyl group replacing one of the hydrogens. Okay, now we're going to treat this with this reagent here, and as an alternate, you see in many textbooks, you could also do aqueous KMnO4 and heat. So it's kind of textbook specific which of reagent they choose to present here, but both of them are pretty good. So as long as our alkyl group has a benzylic hydrogen, we're going to see its cleavage into a carboxylic acid. Okay, the T-butyl group here, however, is unique. There is no benzylic hydrogen in the T-butyl group. All right, I don't know what causes that. I'm going to erase some of these extra lines that I'm getting here. Okay, all right, there we go. No benzylic hydrogen. All right, so what we're going to see is that we're going to see that group, that group, that group, and that carbon. Each one of those is going to become a carboxylic acid. So our product is actually going to be fairly simple. It's going to have a tertiary butyl group right here, 3 methyls. Right here, we're going to have carboxylic acid, carboxylic acid, carboxylic acid, and carboxylic acid. Okay, and that would be the product here. Okay, in this last one, we're going to, this reagent here is halogenation reagent, more specifically bromination. And what happens in this reaction is we take one of the hydrogens on the benzene ring and just replace it with a simple bromine, okay? All right, so all of the hydrogens here, like before, are equal, and as long as we add only 1 mole of bromine, we get the compound here. Okay, we haven't done a mechanism yet here, but let's just, for halogenation. All right, so what happens in the halogenation is we activate the bromine by making a Lewis acid Lewis base complex, like you see there. This is now much more electrophilic. It attacks the benzene ring. Okay, we have a hydrogen now, a bromine, plus here. Okay, and then we'll have another bromine come along and remove this extra hydrogen, and that's how we produce that product. Okay, so those are some good examples of just standard reactions happening in substituted systems. Here there's no question about orientation. That's the subject of the next exercise. But it's always a good idea to be able to, you got to make sure that you can complete the reaction equations before you start thinking about the reactions in unsymmetrical systems. In this one, we're being asked to write a mechanism for the following reaction. Other directions here that we're showing, we need to show all of the resonance forms for the reactive intermediates. If there are any, that's kind of a stupid thing to say. There's actually tons of reactive intermediates here. This is an example of the Friedel-Crafts alkylation in an intramolecular fashion, and I'm allowing the class to show the mechanism with H plus instead of H2SO4 if that makes you more comfortable. I'm going to just compromise here. I'm going to redraw H2SO4 that way so we can see clearly where the acidic proton is. Okay. All right, there's also another hint. Use the lone pairs first. Okay, so a lone pair is in an oxygen or a nitrogen is typically far more basic than is an alkene or a benzene ring. So this is where we're going to see the initial reaction site right here. Okay, all right, so we're going to protonate this. And this is going to give us the protonated alcohol. All right, we see that water is a byproduct here, so let's go ahead and make water in a common way that we see in organic chemistry. Just lose water from a protonated alcohol to make a carbocation. Okay, and here's our carbocation. Okay, let's get rid of that extra line. All right, so here's our carbocation. And if you look at this carbocation, you have to say it's a pretty good carbocation. Look at it. It's tertiary. And it's allylic. And when we say it's allylic, that means we have a resonance structure that we can write. And I'm going to draw this resonance structure here in a way that makes it look a little bit more like the product. Okay. All right, so this is a resonance structure for that carbocation right there. Okay, it's a delocalized carbocation. So these two contribute to the overall structure of the system. Both of these are important contributing structures. If you like the one on the top better, I can tell why you like that, because there's a tertiary carbocation. If you like this one better, you probably are focusing on the alkyl substitution pattern where you have a tri-substituted alkene. All right, when we look at this alternate resonance structure, we now see how the carbocation is set up to make a 5-membered ring here, right? Okay, so if we now go ahead and do the Friedel-Crafts reaction, and we're not using a halide and aluminum chloride. Remember something about the Friedel-Crafts reaction, that any source of a carbocation can actually cause the Friedel-Crafts reaction to happen. All right, so this is going to be our carbocation right here that we get from those set of arrows right there. Okay, the stronger acid in the system, or stronger base in the system rather, is water, not bisulfite anion. So we're going to have water come along, and this is going to now give us the final product. Okay, all right, so we can start any reaction that makes a carbocation can cause the Friedel-Crafts reaction to happen. In this case, we are making a 5-membered ring, and intramolecular reactions that make 5- and 6-membered rings are usually fairly facile compared to the analogous intermolecular reaction. This is an entropy effect, so we'd probably expect this reaction to work pretty well. Okay, this is the last problem on this worksheet. We're looking at the reaction sequence below, and what we're seeing here is that there's a complete failure of this reaction. Compound A there, which looks like the standard product of a Friedel-Crafts reaction, is not obtained to any extent. And remember that these Friedel-Crafts reactions, or any of the electrophilic aromatic substitutions, can potentially happen on any ring that we designate as being an aromatic ring, and this is definitely an aromatic ring. This is a derivative of thiophene. Okay, that's a thiophene derivative, and this can potentially do the electrophilic aromatic substitution. All right, let's think about why A isn't obtained. All right, so let's go ahead and look at the mechanism. All right, so our standard Friedel-Crafts mechanism would involve making the carbocation minus there plus there, and there we go. All right. Now, when we look at this carbocation, we're going to say it's primary. It's not a very stable carbocation, but it also has R groups right beside of it, so it can do potential rearrangement. So it can do a 1,2 alkyl shift. And there's two different compounds that you can get from this 1,2 alkyl shift. This one by a methyl shift. Okay. And the other alkyl group we can shift is one of the CH2 groups of the ring, okay? All right, so we have the possibility to also form the 7-membered ring. All right, so there we go. Either of those 1,2 alkyl shifts could happen. They're probably the first one is more likely to happen because it's generating a 6-membered ring, which is typically a more stable ring system than a 7-membered ring. But both of these are tertiary carbocations, so they're both likely to happen. All right, if we remember the Friedel-Crafts reaction, what we do is we take the hydrogen that's on the aromatic ring and we replace it with the R group that corresponds to the carbocation. So we're not going to get A because this rearrangement here is going to be really, really fast process. So what we're going to see here for B is that it's going to be one of these compounds that results from the alkyl shift, okay? Possibly the compound with an ethyl group attached to the cyclohexane ring right there, or possibly the compound with a 7-membered ring. Okay. Okay, you know that you're really a good organic chemist when you can draw a 7-membered ring. That's when you've really arrived as an organic chemist. Okay, all right. All right, so B could be either one of those two compounds. They both satisfy that side chain requirement, having the formula C8H15. Okay, all right, so that's it for this problem set. We have another worksheet that's going to go on for the next class period, and that one is going to have a lot of unsymmetrical benzene rings that you have to substitute. Plus, there's a lot of reactions where you have to use these reactions in the correct order to get products. Okay? All right, so that's it for this one. I'll just end this one right now. Okay.